Good afternoon, everyone. Thank you for joining us. My name is Marissa Waterman. I'm the Marketing Director here at the Academy. Today's webinar is titled Water Management in Petroleum Industries. Our Executive Director, Dr. Daniel Other, will serve as the moderator and will introduce our speakers today. During the presentation, you'll be able to submit a question by clicking on the Q&A icon on the bottom of your screen. We'll do our best to address each question at the end of the presentation or during the presentation. Before we get started, Dr. Other would like to say a few words. Dan, how are you doing?
I am fantastic. Hey there, Marissa, and welcome to our audience for today's webinar hosted by the American Academy of Environmental Engineers and Scientists. We're thrilled to have you join us today, and I can't wait to introduce our speakers and to learn more from them. But before we get into that, I want to offer folks one final reminder that the Academy is gathering in Washington, D.C. on April 10th, 2025 for our Convocation and Celebration of Excellence. Hence, my hat and my lovely background to remind people of the cherry blossom season. There's still time to get signed up for the event, including to live stream the luncheon technical program and presentations of the awards for excellence in environmental engineering and science. So that's next Thursday, April 10th, 2025. Many of us know that the Academy is known for leadership and excellence, and every autumn, the Academy hosts a summit where we discuss a technical topic, and then we host a transition ceremony where new leaders take the oath of office. To complement our autumn celebration of leadership, every spring the Academy celebrates excellence. For about 3 decades, we've organized the Excellence in Environmental Engineering and Science competition, also known as E3S, where we recognize exceptional projects every year. This year, we're adding something a little bit new. Yes, we're going to celebrate our E3S winners, and yes, of course, we're going to celebrate the winners of our individual awards, but this year we're expanding our event a little bit, and we're calling it a celebration of excellence and a convocation. What does that mean? Well, think about how a university organizes a convocation. We're going for something like that. Specifically, we want to recognize the work of our student chapters. We want to recognize everyone who's been named a member of the 40 Under 40 Club during 2024. We want to recognize everyone who's achieved board certification in 2024. So for this year, we have a luncheon and the E3S Awards ceremony as a technical program, and those are hosted by our friends at George Washington University. Or you can join a live stream of that event. And in the evening, we'll host our first ever convocation. We'll do this at the Marriott in Crystal City, right next to Reagan International Airport, right across the river from downtown DC. The convocation dinner is the place where we'll recognize individual award winners as well as recently board certified engineers, engineering members, and scientists. All this to say, please sign up to join us on Thursday, April 10th, 2025, with lunch from 11 to 3 Eastern and dinner that evening at the Marriott. We can't wait to have you join us. All right, let's pivot to focus on today's main event, which is a webinar by a dynamic duo, Dr. Somnath Basu and Dr. Andy Shaw. If you don't know these two gents, then I highly recommend that you find time to reach out to them and meet with them and get to know them better. Sam and Andy are brilliant, and they're also amazingly nice guys who have always been great friends to the Academy and to me personally. So I'm really excited to be doing this webinar with them today. Before I formally introduce our speakers, let's take a moment to pause and offer a word of thanks to our patrons. Patrons are utilities and firms who financially support the programs of the Academy. Today's webinar includes participation by folks from and associated with Black & Veatch, an Academy patron. B&V has been a patron for a number of years, and we're grateful for their commitment to the profession and to the Academy. And of course, we're grateful for all our patrons shown here on this slide. When you get a chance, please say thanks to these folks for stepping up to financially support Academy programming. If you'd like to learn more about how your organization can sponsor a webinar or get involved as a patron, please let Marissa or myself know. We're happy to answer your questions and explain the value proposition. And now let's get started with our formal event. Dr. Somnath Basu, or Sam, is a technology and policy advisor in environment and energy. His practice areas are industrial waste and wastewater treatment, nutrient control, renewable energy, and the water energy nexus. He was a Science and Technology Policy Fellow at the American Association for the Advancement of Science, hosted by the U.S. Department of Energy in Washington, D.C. just until 2023. His prior affiliations were at Headworks International, Houston, Texas, where he served as Vice President and Chief Technology Officer, the Water and Utility Division of Shell Oil, where he was a member of the Shell Global Solutions team, and Siemens Water Technology, as well as the Massachusetts Water Resources Authority. Sam is a fellow of the American Institute of Chemical Engineers, as well as the Water Environment Federation, where he's the current chair of the Editorial and Publications Subcommittee of the Industrial Water Committee of WEF. He's a member of the Board of Trustees of the Academy, and he has more than 40 years of experience, including publications and presentations in his area of practice. Dr. Andrew Shaw, or Andy, is a global practice and technology leader in wastewater and sustainability for the Academy patron Black & Veatch, and he's based in their Houston office. Andy is the past chair of the Technical Practice Committee for the Water Environment Federation, and up until the end of 2024, he also served on the Board of Trustees for the Academy. He is also a past board member of the Institute for Sustainable Infrastructure, ISI, and Vision. He has over 30 years of wastewater treatment experience on 4 continents, including operation, design, and research. Today, Sam and Andy will be working as a team to present water management in petroleum industries. Please remember, I'll be moderating a Q&A as part of today's event, and it would be great if you would share your questions in the Q&A panel that you'll find at the bottom of Zoom. I'll use those to direct today's discussions. And now, with those instructions and introductions out of the way, Andy and Sam, the stage is yours, my friends. We're so excited to hear from you.
Great. Thanks, Dan, for that introduction, setting us up. Today we're going to talk about water management in petroleum industries. The last couple of years, Sam and I have been working on a book, which we'll talk about a little bit at the end of the slide deck. We'll do a shameless plug at the end, but out of digging in to all the ins and outs and nuances of water management in petroleum industries, we've pulled together a lot of nice material, a lot of good information, and we wanted to share just a snippet of that with you during the webinar today. So let me see if I can get the slides to work. So here's the outline of what we're going to talk through today. I'll start off with a little bit of background on petroleum and the different sectors within the petroleum industry for those who are not familiar with that. Then I'll pass it on to Sam, who will really dig into what's involved in water management in each of the different sectors. And then he'll dig into a little bit on water treatment and wastewater treatment, some of the technologies that are used and some of the drivers. Then he'll pass it back to me. I'll talk about process modeling. That's one of my strengths that I've been involved with. And in the book that we'll mention at the end, I was involved in pulling together the team that developed materials for that particular chapter. And then we'll wrap up with just some very brief conclusions, and then the shameless plug at the end for the book for those that want to go and get it. So without further ado, I'll move into some of the background information. First of all, those who are not familiar with crude petroleum, some of the things we need to think about are the main constituents that are naturally in petroleum as it's been mined and refined. Of course, there are the hydrocarbons themselves. That's what we're after when we get our crude petroleum, from the paraffins, naphthalenes, the aromatics, as well as the aliphatics, and then various other hydrocarbons that are involved in the mix. In addition, along with the hydrocarbons that we do want, we get a bunch of other things that we don't particularly want, such as some organic sulfur compounds. So as we're pulling that out, we've got to deal with that, and obviously some of that will move into the liquid phase. We also have organic nitrogenous compounds that we need to deal with, some oxygenates. We're also pulling up sediment and water along with the oil, so we've got to deal with that as we're producing the water. We produce water as well, and then this, the petroleum's coming out of the ground, so there's a whole bunch of dissolved ionic species, metals and metalloids that are in the water, in the oil, and in the water. So we've got to keep those in mind as we're thinking about water management, what's produced as we produce petroleum. In addition to what comes naturally, we are within the industry adding various chemicals. So we're adding chemicals for antifreeze to stop things from freezing up. We will be adding some chlorinated organics there, so we need to be cognizant of those. And then there will be some amines added to suppress H2S production during transport and in the rail car. So there are additional things that we're are added to the petroleum that we've got to deal with once we get to the refinery in particular. Next thing I just want to touch on was how do we think about the petroleum industry? This is good to kind of understand. Is there are basically three sectors that we've labeled within the petroleum industry. There's the upstream, which is the exploration and production. That's the drilling and production of the oil. Midstream is collecting and moving that down to the downstream, and downstream basically is the refineries. And then sometimes we also include in downstream, in addition to that, the marketing of collecting the produced products and shipping them out to various folks. So at each one of these stages in the business sectors, they have different impacts on the water cycle. And so that's what we're going to move through in the next few slides. I'm going to pass it on to Sam to start with the upstream and then move on through the process and look at the water impacts. So with that, Sam, if you want to unmute yourself, I'll pass it on to you. And you just nod when you want me to go to the next slide. So I think you're muted right now, so we've got to unmute you.
Okay, can you hear me
got
now?
it? I can hear you now.
Okay, great. Thank
Over to
you.
you, sir.
So, yeah. So thanks, Andy. So let's move on to the next slide. Okay, so this is a representation of the sectors that Andy just talked about. So it starts with the upstream, exploration and production. Midstream is storage and transportation, and downstream is processing, refining pretty much. And then finally, marketing through terminals by rail cars or barges, etc. Next slide, Andy. So we are going to start with the upstream part of it. And what are the resources? So this slide shows a very elementary description about the resources. And you can see the conventional resources are up on the top surface, as you can see here, very close to the ground. And then the unconventional resources are the shale oil and gas resources, which are farther deep down, and they are all stored in very, very fine porous rock structure. So this gives you a background of what kinds of petroleum resources are there, conventional versus unconventional. Next slide, please. Okay, I'll go through this very quickly. So essentially, for conventional production, as the petroleum crude comes out from the ground through the wells, and then it goes to separators, and this is a three-phase separator where you can separate oil, gas, and water. And water, you can see from the bottom, it goes to the processing stage, and then finally it is disposed. And currently the major disposal means is injection into the ground. And other than that, you can see the oil that is processed and it goes to the desalter, and I'll describe the function of the desalters. Also, please note that desalters are not very common in upstream industry. There are some sites which use desalter, but other than that, primarily it goes straight into tankage and from there transported to the sales and marketing segment. And then the gases, it goes to some gas processing, gas dehydration, and then it goes for the pipeline. Next slide, please. Okay. So as I said, the two major distinctions are conventional versus unconventional in the upstream sector. The conventional, as I explained, is up near the surface, and it is the water treatment part of it is fairly straightforward. It's just it contains mostly TSS and some oil and grease. So water goes through flotation, and and then water first goes to gravity separation by API and CPI separators, and I explain those later in this presentation, and it goes through flotation like DAF, DGF, IGF, etc. And again, I'll explain those later on, and then media filtration, and then it goes to the disposal oil and disposal well. And whatever solids and liquid hydrocarbons are separated from the API and flotation units, those are sent to a wet oil tank or slop tank, and then they are sent to the recovery unit and sent back to the crude storage system. Next slide, please. Okay, the conventional offshore production, it is very similar to conventional onshore production, except for the fact that the footprint is very limited here. There is very limited space because these are all located on the platforms, and these are platforms in the deep sea or ocean, so they are footprint challenged. That's why you can see in many cases they use cyclones or hydroclones as opposed to API separators, which use a lot of space because it's basically gravity separation. And then the compact flotation unit, instead of DAF or DGF, typically IAF is used, and I'll explain why the difference is. But induced air flotation units are used, which consume less space. And again, the water is sent out for disposal, and in this case the disposal is overboard, so they are disposed into the ocean or into the wells underneath the ocean. So in this case, in most cases, it is disposed into the ocean. So there are many regulations that regulate the quality of the effluent. I'll come to that later on. And then let's go to slide, Andy. Okay, now the second part of upstream production is unconventional production. That's by hydraulic fracturing, and you must have heard quite a bit about hydraulic fracturing. And just to give you a perspective, in the US, about 85% of the production is by unconventional production. And a major part of that, I would say maybe 90% of that, is by hydraulic fracturing. And there are three major shales or formations in the US that contribute to this abundance of oil and gas in the US. I can remember back in the 1990s or early 2000s when US was building some ship channels for receiving crudes from Middle East and other countries. Now, with the advent of the upstream production methods, particularly you can see the hydrofracturing, where the water is sent at a very high pressure and very high velocity, so it can break up the rock structure, the shale structure. And in this case, the oil and gas is trapped in the very, very fine micropores of this rock structure. So it's very difficult to tap out oil from there. So, and this was invented by a gentleman by name George Mitchell of Dallas, Texas. And hydrofracturing releases the oil and gas, and you can see the simplified version. And so water is sent here at high velocity that breaks apart the rocks and that releases and also the lateral fracturing mechanism. This is one view you are seeing, but from this vertical down pipe, there are many such branches that go all over the place, all over the section of this rock structure, and it covers something like 2.5 to 3 kilometers in radius around one vertical pipe. So you can imagine Mexico is the Bakken Shale, North Dakota, Wyoming, and up in Canada also. And then the third one is Permian Basin, which covers a major part in West Texas and New Mexico. Next slide, please. Andy, can you please move the slide? Can you please move the slide, Andy?
Is it moving? I moved it my end. It might be laggy your end.
Okay, I do not see it.
You seen shale gas situation, Dan, or are you still?
Yes, shale gas
I-
plays lower 48 states.
I think you're laggy your
Okay.
end.
Okay, then I go to my slides. Then.
Yeah. So we're just showing the different shale
Yeah,
gas
this is
areas which you'd
and
already got.
again this goes back some 10, 12 years. So
Mhm.
I'm sure this has been updated by EIA, but this is what I had.
Mhm.
And so you can see Marcellus Shale on the northeast corridor, and
Mhm.
then Bucket is up in North Dakota, Wyoming area, and then there is Permian Basin in Texas, West Texas, and New Mexico.
Okay.
Okay, yeah, I can see the. Okay, then the next one. Okay, so when I said that water is pushed at a very high velocity, then it's not just water. You can see this is the composition of frac water. Okay, frac is the short term of hydrofracturing, and people in the industry very fondly call it frac. So you can see at the bottom of this table, water is 99.5%, and there are various other constituents, but each has its own function. And you can see the role of each of them. And one of the most important thing is guar gum. And basically guar gum is used, which is which is used, this is a gel, and this is used to suspend the propents. Propents are sandy particles, very fine
Mhm.
sand or silica particles, which are suspended into the water, and that goes and hits these rocks to break them apart. So you can see each of them has a purpose. So I'm not going to go into the details, and we can discuss this at the end. And you can see what is the water footprint in upstream operation. Frac water, then flowback water, where flowback is some of the frac water and some of the produced water. What's the difference? Now, flowback is when most of the frac water returns along with some produced water. Produced water is the kind of water that is also called connate water, CONNATE, connate water. And that is the kind of water that is native to the rock structure. So it comes out with the crude. So it is not something that is injected from above ground. And you can see I have the list of the constituents or characteristics of produced water, and the TDS is extremely high. Okay, you can see high concentration of sodium, high concentration of chlorides. So it is very, very saline. But along with that, there are some very important constituents that one has to consider while coming up with some technology for treating
Mhm.
the upstream produced water. And those are the divalent cations. Particularly, it is very critical at Marcellus. It has barium, calcium, magnesium, those are all hardness divalent cations. Also, barium and strontium, those are also divalent cations. And why they're important? Because they tie up with sulfate ions, and when they react with sulfate, they form hard scale that is very difficult to remove. And that's
Mhm.
why in produced water treatment, removal of divalent cations is one of the important steps. Next slide, please, Andy. Okay, you can see the the production flow diagram, and I'll not take too much time, but after equalization, after the separation, the primary separation and separation of oil and gas, and then water stream that comes to the equalization and flotation by, as I mentioned, not DGF or DF, it is by IGF or DGF, and primarily by IGF, and then electrocoagulation or some form of coagulation to flocculate the solids, and then you have to treat it with lime soda process. To if there is uh, a lot of calcium and magnesium hardness present, then you have to treat it by lime soda process, followed by a treatment by sodium sulfate, and sodium sulfate reacts with divalent cations barium and strontium to precipitate them to form solids of barium sulfate and calcium and strontium sulfate, so they can all settle in the gravity clarification step, after which the water is ready to go to biotreatment. But I can also tell you biotreatment is very uncommon in upstream produced water. This slide presents a very generic view, and not all the treatment unit operations and processes are applicable to each type of produced water at each site. It has to be decided on a case-by-case basis. And after that, clarification and filtration, and then evaporation, crystallization, or RO if tertiary treatment is needed. In many cases, it's not needed, but I'll explain you later that regulators are asking the operators to move away from the underground disposal. What is the option? The only option is you recycle and reuse it. And for that, the steps to be taken are evaporation, crystallization, or UF and RO. And then we'll explain that later on. Next slide, please, Andy. Okay. So to summarize, two main classes of production, upstream production, unconventional and conventional. Now, I described in detail the conventional, onshore and offshore, unconventional hydrofracturing or fracking. Now, what I did not describe is thermal EOR, thermal enhanced oil recovery. And this is mainly applicable to the oil, the rocks that are mined in the Canadian Rockies, and they are semi-solid, very hard, and they don't move, very high viscosity. So you have to do thermal treatment by steam, or in certain cases in situ combustion in the formation sites to make them liquid enough so they can be transported by piping or by other means of transportation. Now, here also the water treatment is challenging because you have to have a boiler unit on site to produce steam. And in order to have the water of the right quality for feeding into a boiler, you have to have the water treatment system that can produce the boiler quality feed water, which produces steam that is used in thermal EOR. Next slide, please, Andy. Okay, the next one is downstream and marketing. I skipped the midstream because that has to do with transportation, and there is not much water or wastewater treatment there. So next slide, please. Okay, so downstream operation mainly is petroleum refineries, where the crude is processed to produce valuable products, which we use day to day: gasoline, naphtha, diesel, and of course gas, which is the lightest fraction. And you can see the slide again, the downstream part of it, downstream, and then the products are sent out to the market by barges, oil tankers, and then pipelines, and by oil tanks, tank trucks. Next slide, please. Okay, now in case of downstream, we have both water treatment and wastewater treatment, and this is the on the right hand corner is the block flow diagram for water treatment. I'm not going to go through it. It's a little bit, it seems a little bit complex, but let me explain what the main water streams are. Stormwater handling and disposal. Stormwater in most cases is clean water. It doesn't have to be treated. So it is either entirely oil-free, but the stormwater that falls into the process units like distillation columns or the places which have uh, which have sheens of oil, they are called accidentally oil contaminated water. When it is entirely oil free, let's say from the office buildings and from the areas which are totally away from the actual refining unit operations and processes, they are sent to uh, mostly they are stored for later use as utility water or fire water or even makeup for boiler and cooling tower. But if it is accidentally contaminated, it is sent to reservoirs and then it is tested for COD and other contaminants. And if it is hydrocarbon free, then it is combined with EOF water and then it is sent to the proper disposal and use. Then fire water storage and handling. This is very important, and they have most of the refineries have their own impoundments to store the stormwater, rainwater, and water from other sources like lakes or nearby rivers. So, because in case of a fire or accident, fire water is very important to prevent and to mitigate the situation. So that's very important. A side note, they use the chemicals that are PFAS laden. So there are incidents where refineries have to remediate the groundwater PFAS or to treat PFAS. That's just a side note. And then river or seawater, and in most cases, river or seawater is used for cooling, once through cooling purpose. If a refinery is next to a sea or ocean or even a lake, sometimes they choose to use uh, river water or seawater in once through mode because cooling tower maintenance, and I'll come to that. Cooling tower takes a lot of water, a lot of fresh water for makeup. And you can avoid that by using river or seawater. The only limitation is, and it varies from state to state, then community to community, how much delta T, what is the upper limit of temperature that you can discharge it. Typically, it is 5 degrees C. You cannot discharge something that is above 5 degrees C of the mainstream of river or sea, but it varies from place to place. And then feed water. The feed water treatment, mostly feed water sources, city water or river water, groundwater or surface water. And then it is used for cooling tower makeup, and then the discharge is blow down. It is used for demineralization for boiler because steam is intricately connected with the operation. It is an indispensable utility in any refining operation. Then condensate policing, and this is the condensate coming back from the process condensers, which is polished to get rid of some of the contaminants it has picked up, and then again sent to the demineralization loop. And then boiler makeup, boiler demineralization, and then the boiler blowdown to the waste treatment plant. And there are two streams which are called process water streams, and I'll explain what these are. These are called sour water, uh, stripping waste, and then desalter brine. And then finally, wastewater. This is the total water footprint: primary treatment, secondary treatment, and tertiary treatment, leading to final polishing. Next slide, please, Andy. Okay, so you can see the water used in refineries, and I just mentioned the blowdown, which is to the wastewater treatment plant. So it is lost, and that is a huge consumption of water. And then the next is the boiler feed water. So, and then there are other consumers also in sanitary water. And why do we need sanitary water? Because where will the employees go? They need sanitary water for drinking, cafeteria. So all that, typically the sanitary water discharge is not sent to the processed wastewater. It is typically handled by a packaged plant on site. And that's true also in case of offshore treatment, offshore in upstream, where the employees, the personnel, the waste and the cafeteria waste are treated in separate package plants on the platform. Next slide, please. Okay, now this is a very familiar slide. Now, when there is the water is pretty clean, it comes from a lake or surface water. It just goes through the traditional process train, and coagulation, flocculation, and then sedimentation, settling sedimentation, and then it goes through a multimedia filter, and it feeds the advanced treatment steps. What is advanced treatment? Now let's say the source of water is groundwater, which contains a lot of reduced um, reduced iron and manganese in the water. Then, as you know, when iron and manganese from groundwater, they come in contact with atmosphere, they get oxidized, and they form particulate matter which settles in the downstream units, and you cannot use that. So that's why first they have to have some aeration step to remove those dissolved iron and manganese as particulate matter, and uh, then uh, you have to remove the hardness also. In case there is hardness, then you have to remove the hardness of calcium and magnesium, and then you go through the flocculation step, filtration, and then before feeding it into the boiler feed water system or cooling water makeup system, you have to go through, I have it as RO stream. Both RO and ion exchange and a combination of both are used for feeding it into the feeding water into a boiler feed system. Then the next slide, please. These are the pictures of some of the units that are used, and these are same. This is same as domestic water treatment. So top there is the hardness removal. It's a traditional lime soda process, and then recarbonation by adding carbon dioxide. So that's the only thing I would add there. Next slide, please, Andy. I guess it's not.
Is it lagging a little bit? We've got water demineralization as the next topic. So
Okay. water demineralization. And here the
Mhm.
demineralization is done by ion exchange or RO, as I said. And ion exchange is very dominant and very traditional in case of refineries and thermal power plants. And it consists of treatment train for cation removal and then decarbonation to remove CO2, then anion removal for chloride, sulfate, etc. And then final polishing mainly for silica removal and any residual anion and cation that are carried over from these two sets of exchangers, cation removal or anion removal. And the regeneration is done periodically by caustic for cation removal and sulfuric acid for anion removal stages. And they are all released to the wastewater treatment plant after pH neutralization. And then RO process, one or the other or a combination of both are used. So RO is preceded by UF to remove suspended solids and then RO to remove the TDS, the dissolved solids and salts. Next slide, please. So these are the some examples of the membranes that are used. I'm not going to go through that. It is very similar to domestic wastewater treatment for that are used for recycle and reuse purposes. Next slide, please, Andy. Uh, Marketing. Uh, okay. So, Andy, I don't see the wastewater slides here.
Okay, next one.
Yeah, I see the wastewater slides. Okay. Okay. So the this is the crux of the secondary treatment. So basically, refinery wastewater has two levels of treatment: primary treatment and secondary treatment. I must say this: primary treatment is very, very important in case of refinery wastewater because there is a lot of contamination by oil, by hydrocarbons. And if there is passage of hydrocarbons into the biological treatment, then the whole treatment process fails. And there are many such examples. So, bringing the oil and gas, I'm sorry, bringing the hydrocarbon concentration to anything below 50 milligrams per liter, the lower the better, uh, prior to entry into the into the biological treatment. That is very important. And there is this is table for biotreatment influent. And although just BOD removal or COD removal is the traditional process, but more and more regulators are asking for nitrification, ammonia removal, because there is significant amount of ammonia associated with refinery wastewater. And some are going all the way for total nitrogen removal. Next slide, please. Okay, here it is. Okay, so in the downstream, there are two places, two unit processes or unit operations that use process water and that produce waste that go to the refinery wastewater treatment plants. Now, one is sour water treatment. What is sour water? Sour water is something that contains large concentrations of H2S and ammonia. Where does it come from? In refinery operations, in various distillation columns and reactors, there is the sulfur compounds, the organic sulfur compounds and H2S come out come out with the products. Now, these products, let's say you use gasoline or diesel or even fuel oil that has high concentrations of sulfur compounds. When you burn it in a power plant or in an internal combustion engine, all those emit as SOx. And because of the regulations the tight regulations controlling SOx air emissions, the refiners are having to sulfur in the crude that comes with the processing steps. And what is the removal? The removal is done by something called hydrodesulfurization. In a reactor, it's a catalytic reactor. The catalyst is traditionally nickel catalyst. These days, the refiners are also increasingly using the the higher grades of catalyst containing platinum, ruthenium, rhodium type of catalyst. So, but the end goal is to convert all the organic sulfur compounds like mercaptans, thiophenes, disulfides into hydrogen sulfide. That's a catalytic process. So after that, after desulfurization, the refined oil or processed oil goes through another step where H2S is separated, and it is separated by steam stripping, and with steam comes out the H2S. And when you treat it with hydrogen, the organic nitrogen compounds are also converted to ammonia. So it is highly ammonia and H2S concentrated stream, which is called sour water stream. And it goes to a sour water stripper because if you discharge all the H2S into the wastewater treatment plant, no operator will approach that. It is not only odorous, but it is health and safety wise, it is very risky. So it goes through a stripping process, and the stripper, it is a steam stripper. The off gas, as you can see on the top, that goes to something called a sulfur recovery unit, where the off gas goes to a catalytic unit where H2S is partly combusted to produce sulfur dioxide, and sulfur dioxide reacts with H2S to produce elemental sulfur, which the refiners sell as sulfur that goes to sulfuric acid manufacturing plants. So that is the sour water stripper. So stripped water, that is more manageable, and that goes to the wastewater treatment plant. Now there are variations. One is single stage versus two stage. Two stage is a Chevron process. Currently, it is licensed by Bechtel. And in two-stage process, the first stage is hydrogen sulfide, where acid is added to release all the sulfides, dissolved sulfide as H2S to facilitate that. And then in the next step, caustic is added and to release all the ammonium ions to ammonia and ammonia gas, and that goes to a separate ammonia collection system. Next slide, please. Okay, the other unit, the process water, where process water is used, is a desalter. And in the desalter, the crude as it comes from the ground, before it goes to any processing unit in a refinery, it first goes through the desalter. Because as I stated before, crude contains a lot of salts, and you cannot allow that salt to go through the refining and downstream processing. You have to remove the salt, and that salt removal is done by desalters. And here, water is injected at a high pressure to mix up with the crude, and the separation of it has two functions. One is desalting, and the other is separating oil from water, because the aqueous phase, the water that you inject, that dissolves all the salts. So, so it separates the crude into an oil layer at the bottom and water layer at the top. The water layer goes to the saltwater stripper where it is used, or where it is used to remove H2S, or directly to the wastewater treatment plant, and the oil layer is fed to the crude refining units, the atmospheric distillation column. So that's the fate of the two layers. And so you can see it's very important to have this desalting. And why it is important? Because if there is carryover, and the separation is very important between oil and water, because if there is carryover of water with the oil phase, that oil will carry a lot of water, and that adds high thermal load to the distillation columns downstream. So that adds to the operating expense. And if and also all the salt that is carried over to the crude column, that can corrode the trays in the column. So it's very important to have a good separation. And then the oil, the oil layer, that's the oil layer, but the water layer, if it carries a lot of oil, then that will end up in the wastewater treatment plant, and that becomes very difficult to treat. Next slide, please. Okay, so this is the schematic of the desalter units. It can be single stage or two stage. With single stage desalting, you can remove up to 95% of salt, and with double stage, you can remove up to 99% of the salts. Next slide, please. This is a picture of a desalter unit. Thanks to Forum Energy Corporation, they gave us this picture. Next slide, please. Okay, so what's wastewater treatment? The wastewater treatment has two main steps: primary treatment and biological or secondary treatment. Now, again, primary treatment, as I mentioned, is the function of primary treatment is to separate oil, remove oil from water. And it is done in two steps: primary oil water separator, which is API separator. Mainly it works on the principle of gravity separation, like a clarifier. The only difference with a clarifier is it handles a lot more oil. And typically you can see oil is present in wastewater in three phases, which is the free phase oil. A large part of the free phase oil is removed in the primary separator, API separator. Then dispersed phase, which is the emulsion, which you cannot remove by gravity settling. And there you have to use the DAF or IAF, induced air flotation. And then after equalization, it goes to biological treatment, and then it goes to tertiary treatment and disposal. Next slide, please. Okay, this is a picture of the API separator. It is very similar, as I mentioned, to a clarifier, handles a lot more oil. And so these are the parts, and you can see it removes bulk of free phase oil droplets more than 150 micron in size. And the influent oil and grease concentration can be anywhere between 200 and 80,000 ppm. But the effluent has to be limited to below 200 because it is fed to the secondary oil separator. Next slide, please. The secondary oil separator of the primary treatment is by DAF or IAF. Now, what is the difference? The bottom left corner shows a graph of the bubble size and the distribution of the number of bubbles. And why is it important? Because DAF has to have, or DGF has to have between 10 and 100 micron size of bubbles to be effective. And in case of DAF, it is dissolved air. So air is saturated with the DAF effluent, the treated effluent from DAF, and then it is released as it enters into the DAF unit. So it is released in fine bubbles, and those bubbles attach on their surface the fine emulsified mist of oil droplets. So, and the effluent has to be around 25 milligrams per liter. As you can see, IAF or IGF has uh, has higher bubble size. And what is the difference? The difference is that in case of DAF, it is dissolved. In case of IAF, it is mechanical. It is mechanically air is dispersed by uh, by some eductor or by mixer, by mechanical mixers. That's why the bubble sizes are different, and so is the separation efficiency. But still, IF and IGF are used in particularly when the footprint is challenging. And why gas flotation versus air flotation? Because uh, as you know, refinery emissions are very much restricted. So when it is air flotation, it goes, the emissions go directly to air, and it just does not fulfill the air permitting requirements in many cases. So that's why the dissolved gas flotation unit, they use nitrogen as opposed to air. But these are covered, and in case of air flotation, it also can create, you cannot cover air flotation because on the headspace, it creates explosive vapor. And so it's very risky. And also, oxygen is corrosive. So, from that point of view, the gas flotation is much safer. It does not create corrosion problem, but it has to be covered. And then the gas that comes out has to go through a carbon canister or some sort of air pollution control unit. Next slide, please. Okay, biological treatment is the last unit process. Now, as you can see, lagoons, trickling filters, uh, these are fixed film processes, and mostly lagoons are present in very old refineries, but they require large real estate, and many of the refineries, because of their space crunch, they are coming out of lagoons and they are getting into more advanced type of treatment, typically activated sludge process. But lagoons and trickling filters and RBCs also are used by old refineries. Trickling filters, it's one of the examples is the Deer Park treatment plant, Deer Park refinery in Houston area, where they use trickling filter. It shaves off 30% of the COD upfront of the activated sludge process, and also it reduces the temperature because the wastewater temperature is upwards of 40 degrees C. It has to be brought down for effective activated sludge process. So it is brought down to below 35 degrees so it can be biologically treated. And then, of course, our old friend, conventional activated sludge, and that's the workhorse for refinery as well as domestic wastewater treatment. Next slide, please. Then many of the refineries, particularly grassroots refineries, are going more and more into newer processes like MBBR and MBR. I'll not go through the details, but MBR, the main driver is to be able to reuse, because after MBR, they use RO, and then they reuse it for recycle and reuse it for boiler feed and cooling tower. Next slide, please. Okay, tertiary treatment. Now, why tertiary treatment? What are the drivers? The two main drivers are, as you know, refinery wastewater contains a lot of chemicals. So they may be driven by the regulatory requirements, or the other drivers is reuse, as water supply is becoming more and more limited. And we have shown three typical processes. Filtration is common with every refinery because once in a while the activated sludge process goes through filament problem, particularly nocardia problem. If there is a lot of slippage of oil from the primary treatment, it ends up in activated sludge process. It creates nocardia, and refineries operate at very, very high SRT, 30 to 40 days of SRT. So it creates the flux that don't want to settle. So most of the refineries has the filtration systems to arrest any passage of solids so that they can comply with the regulations. GSE, the main purpose is to remove organics that may be toxic and that may not be in compliance with the requirements, the regulatory requirements. And then, of course, advanced treatments to remove any metals that may get carried over, because metals are not arrested by any of the treatment processes upstream. And in and I would like to mention here the regulatory requirements are becoming stricter and stricter, and there is something called wet testing, and that has to do with it is the toxicity testing, and it is a part of every refinery NPDES permit. So it has to go through some tests to make sure that it does not kill, it has an EC50 value. It does not kill the aquatic organisms. So you can refer to wet testing, WET, wet testing. So for that, there may be metals that may affect that, mercury, arsenic, selenium. So those treatments have to be done as advanced treatment in tertiary treatment steps. Next slide, please. Okay, Andy, please take over.
Okay, thanks, Sam. So you can see there's a lot of detail and a lot of different processes within petroleum processing. So we have a lot of different types of water streams, different levels of contaminants. So I just wanted to spend a little bit of time touching on some of the tools that are available to understand some of the different transformations and treatment options. Process modeling, one of the very useful applications for process modeling is understanding the scaling potential that we have. So as Sam was talking through, particularly the unconventional treatment, looking at fracking water, it is a high propensity for causing scaling. And if you try to do a hand calculation or a spreadsheet-based calculation to understand, okay, what level of scaling am I going to get? You don't get very good results. It's very, very inaccurate, very imprecise way of trying to understand what's going on in the system. Because of that complex speciation of all the different metals and metalloids that are present in the water, it's very difficult for the calculations to be done. So therefore, going into a model-based approach to understanding the water chemistry and the potential for scaling is a much better approach. So that's one of the applications of using a process model. I'm showing one here from OLIsoft. That's one of the providers of this kind of software. So they've got a very nice tool to be able to look at scaling potential based on the complex water matrix that you may have. Another application of process modeling, a little bit more straightforward, but again, trying to understand the water chemistry is looking at the sour water stripper that Sam was talking about earlier. It's kind of understanding, okay, what is going to be the fate of my different constituents, or particularly my H2S and my ammonia, which stream is it going to go in? And then how do I size and optimize my stripper column to get the right kinds of removals. So again, tools are available to be able to do this using a process model, which is a much faster and more accurate way of doing it than doing a hand calculation. Finally, I just want to touch on something that's near and dear to my heart is process modeling of biological treatment. If you look on this little diagram in the bottom right-hand corner, we've got processes there for biomass growth, decay, hydrolysis. Those are very familiar to anybody doing municipal domestic wastewater treatment. The IWA activated sludge models, 1, 2, 3, they were very much focused on those processes, the biological processes. as we move into industrial wastewater treatment, particularly in petroleum industry, we also need to be thinking about volatile components, so the volatilization, and then we also need to be thinking about adsorption of the different types of components, different oil-based and colloidal type components. How will they get entrained and processed by the biology? So it's biological models as a whole are pretty complicated, and then as we add on the industrial aspect to it, it gets even more complex. So having a simulator to be able to do that is a great boon. It's real help to us. I'm just showing one of the simulators that's available to do this. The Hydromantis guy, the Mantis industrial water model. They've built this over the years. Very useful tool to look at your biological treatment. In this case, they were looking at the sizing of their bioreactor to get the right solids concentration and the right effluent quality, so you can use your biological model to kind of do some optimization of your design there, or troubleshooting. You can also do that with the process models. So in wrapping up the discussion that we've had today, we know that water is vital for life. And as you hopefully got a flavor for through the presentation today of the details that Son's gone through, that water is a huge part of the petroleum industry. So different water uses, different wastewater products that we have to manage and handle, and we've got to manage it well, particularly as we're looking at the unconventional extraction of petroleum products. The produced water there is order of magnitude more complicated, more difficult to manage. So we need to know what we're doing with those different water streams, and we have the technologies and the means to do the treatment and to manage it well. Did you want to add any thoughts on this, Sam?
Actually, I very briefly on the regulations. That's a big part of petroleum industry,
Mhm.
and also the as I mentioned, wet testing, and I didn't go into the details, but uh, we can explain it later on offline because it is a subject by itself. But WET, that's very important. That's a toxicity test. Now, also the reuse is becoming more and more common in refineries because you can see the makeup water, boiler feed, and cooling tower makeup water. Those waters don't come back, so they cannot be reused. They have to be disposed. So they add to the burden of the wastewater treatment plant and the cost. And as it is, water is in shorter and shorter supply. So the governments or the states are asking the refiners to reuse as much as possible. Now, in this case, for downstream sector, reuse is already happening quite a bit. And I can give you several examples, like Chevron refinery at various places are using MBR followed by RO, so they can reuse it. This is in Singapore refinery. This is in El Segundo, California refinery. There are various other places where they are reusing the downstream wastewater, and I think in Los Angeles they are taking the wastewater from the municipality, the effluent, and they are using that as makeup for cooling water. So that's also another type of reuse in downstream. More challenging is upstream because the water in let's say Permian Basin, it has so high salinity.
Mhm.
How can you reuse it? So right now they are pushing it into the ground, but that's going to stop very soon because Texas Railroad Commission is coming up with new regulations. If they have not already done so, I have not kept track. So, uh, what are the possible processes? The only processes are RO because this is all inorganic. Only processes are RO and evaporator crystallizer. The water that comes out from these processes are very high purity water. So it can be used for agriculture, for irrigation, or they are also thinking about using that water for hydrogen production on site as a fuel. But even after that, you have how much from 200,000 milligrams per liter of brine, how much can you concentrate? You get about 50% of product. Remaining 50% you still have to push into the ground. So that
Right.
will reduce the number of injection wells. The other thought is to use it as a feed material for caustic chlorine production, because that's how caustic and chlorine are produced from sodium chloride solution.
Okay, I think we may have lost some. Can you hear me, Dan, still?
I
Yes,
still
we
hear
can
you,
hear
no
you.
problem.
Okay, I think we lost some. So we're just talking through. So we're pretty much at the end of our presentation. I did just want to touch on the book that I said I was going to do a shameless plug. So here is that shameless plug. So Somnath and myself and Mr. Venkatesh, we worked on this book, Water Management in Petroleum Industries. We were the editors, but we had a lot of contributing authors. So I think Som pulled in a lot of favors here to get a lot of good people engaged, involved in what is quite a complex problem. I'm very pleased with what we've produced here. So it's a very nice book for you all to take a look at if you're interested in any aspect of water management in petroleum industries, from water supply, water treatment, all the way through the wastewater management and handling. So the book's not quite out yet. It should be out this month, end of this month, early next month. But there's a link there. You can go and pre-order or check it out. With that, thank you for your attention. I guess Sam and I, we could try turning our cameras back on. Let's see if that
Yeah,
works.
yeah, appreciate
go.
it. So yeah, and if we pull this, if we stop share, then people will be able to see us a little bit bigger. That's always kind of fun.
Okay,
So
let
they can
me
kind of see a little bit more
stop
discussion. Would be
share.
great.
Stop share. There we go.
Awesome. Thanks, Andy. Well, I think we still got you there, right? Okay, there, he's still there. All right. So I'm gonna lay out kind of some questions, kind of categories and kind of big questions, and then we'll kind of come back and walk through them. So so some of these are my own thoughts, some of these are ones that came in from folks. So I'm still watching those as we're talking through this. So back at the beginning, we think about this kind of like from a water cycle standpoint. So there was those streams, right? The upstream, the midstream, the downstream. So with some questions about spillage and rainfall. So you mentioned some of that, right? But you mentioned some of like the rain coming in, but what about the spills, right? Because I mean, this material, if it spills and goes out, so drive by these things, there's always these berms and all this stuff around it. That's probably got to have some pollution prevention, sustainability thought in it from the beginning with the design. And then in particular, we think about these being in coastal areas. So we might think about, hurricanes dumping a lot of water in there. So how does the larger water cycle fit into particularly thinking about the upstream, midstream, and downstream when you're dealing with petroleum water? So that was kind of a water cycle question. Another is, well, so we'll just kind of go through these some and then we'll come back and pick them up, right? So another was in this notion, Andy, you referred to it as mining and refining petroleum, which is great, right? And then Sam kind of explained to us that actually in the US, a lot of it's now is the unconventional. So it's kind of weird, right? We have this conventional title, but it's not really the one we use, right? We do most of this with the unconventional. And so are we thinking about it the right way? How we prepare our students? Are we misusing the name? Should we change the name so that people aren't kind of, when they hear about it the first time, kind of confused? Or how do we help the public understand about this? And then some sustainability questions kind of at this level, right? Like you hear this anecdotal, right? Like let's turn corn to gasoline and gasohol, and people say, well, it takes more energy to make. You got to put more than a gallon of gas in to get less than a gallon out, right? So there's all these studies that people see. Well, how about like when we're doing this fracking and we're getting this alternative sources of energy? This isn't just pump straight oil. This is, we got to put a lot of work in to get it out. So what's the energy calculation look like from a sustainability standpoint on some of these alternative ways of extracting energy? How does that calculate out? Then when we get into the frack water itself, you talked about the different kinds of it, what's going on there. So it looks like there's a lot of ions in those solutions, right? So how about getting some of those out that might be particularly useful? You've mentioned a number of them, but one of our colleagues mentioned particularly lithium from Marcellus gas play, up to 10 milligrams per liter. We know lithium's kind of a useful thing. So are you aware of anything with lithium? There's talking about other ways of doing some cost-effective reuse of some of that water. Some of the solids seem to be some of the problems. And then we have a very, very specific kind of technical question about sodium hypochlorite to oxidize facilities, refinery, wastewater discharge. We'll get into the specific technical question when we're in this category, so I won't read it twice, but there's a detailed technical question. And then while we're starting to think about the refinery and the water uses there, so you had this nice pie chart that talked about water use in refineries. A number of folks were wondering, do we have a reference for that? Because some people were like, hey, that looked like a great piece of information, so can we get a reference? But also unaccounted, that was like the third highest, right, at 15%. So do we have any idea what that means? What proportion of oil, gas costs are associated with all these supplementary water treatments and dealing with the frac oil or the frac water and the recycle water? And then kind of an out of the blue sustainability questions, right? So we think about, the dissolved stuff, right? The BOD, the ions, all that. We think about like the water itself, but how about the energy, right? So if we're using all this water to be like a one-off heat exchanger, why not use that heat to do some of the extraction in the first place? So should we be doing kind of micro refining right where we're doing the fracking, right? Like let's not waste the heat of refining and dump it into the environment. Let's just dump it back into our process. So from a sustainability standpoint, what does the energy balance on the heat look like, and why dump it into the environment? Why not include the heat as one of the things that could maybe be incorporated back into our system? This goes along with the idea of where can renewable energy be brought into the question. You mentioned, these ideas of materials that could come out, right? So, of course, gasoline used to be the nasty byproduct of petroleum, right? And then now that's the main thing we want, or a lot of it, what we want, right? Awesome to talk about the sulfur coming from the sour, gas treatment. So what other kinds of things are in there, and are we shifting, right? I mean, if one point in time it was petroleum and then it became gasoline, are these other things actually starting to compete with gasoline as we move to electric vehicles? Like as we look over the horizon, will the refining of it start to be more and more important to get all these other side streams, maybe not so much the gasoline? And then we had some specific questions that came in here about the wastewater treatment, right? So, are there particular regulations that talk about the effluent requirements? What are the regulatory requirements? We're running this through biological. Things like BTEX and other things might be, inhibitory for the biological. You mentioned whole effluent testing on the back end. But then a kind of a technical question, Andy, that might fall a little bit more into your bailiwick as well, though. But meso or thermophilic anaerobic granules, right? Like you've got high temp, you've got high organic. Why cool it all the way and dilute it all the way down to activated sludge? Why not treat it at a higher temp? And then, final questions, of course, would be advice for folks that are looking for this as, hey, my career, I want to get into this area, or second career or extra area. What else do they add to themselves to be able to get themselves into this space? So that's the kind of stuff to talk through. A lot there. Right. There. We'll go back up maybe to thinking about this whole cycle, right? So there was the upstream, the midstream, the downstream, but then there's the water cycle. So there's going to be spills, there's going to be hurricanes. Can you talk to us in the broader water cycle? Help us understand.
Andy, I'll address that. In general, Dan, especially in refineries, there are large storage tanks, and each storage tank is protected by a berm or dike. In case of a spill, the dikes are sized in such a manner that everything is contained within the dike. Also, the dikes are meant to capture the rainwater or stormwater, because it is assumed that rainwater, when it drops on those tanks, they get contaminated. So dikes are there to store that water, and they are released only when this is one of the AOC, accidentally um, oil contaminated water. So after testing for COD and other contaminants, they are either released to wastewater treatment plant or they are released back to the environment. So that's that. And in case of hurricanes, for example, because I live in Houston, so I have experienced most of the refineries, they close down. In case of even the power outages, whenever there is a power outage for an extended period, they just close down. They wrap up everything and close down.
Mhm.
So that's the best. I think if there
Yeah,
is a safety professional in this conversation, he or she may chime in. I don't know much about the
yeah.
safety.
I guess,
That's a
I guess,
huge area.
yeah, I guess one other, it's slightly anecdotal, Dan, but my own kind of observation on managing and keeping our petrochemicals out of the natural environment. The larger players are generally doing a decent job. The regulations are there to stop it, to prevent it, to protect for it. Where it's a little more challenging is policing the smaller entities. So whenever, again, having lived in Houston for the last 7, 8 years, whenever there's a thing on the news about there was, a release or something went out into the environment, there's been a handful since I've been here. It's always some small company. It's never a Chevron or Shell or someone like that. Now, not saying never happens, it can happen, but it's more the smaller entities where it's harder to police and harder for TCQ to kind of keep a handle on what's going on there. So.
Makes sense.
And also to add to that, health and safety is a big component in most of the large companies. And I personally used to work for Shell, and
Mhm.
they would put aside some of the very urgent needs for the technical processing if it compromises with the safety culture.
Mhm.
And and I had to go through quite a bit. I had encounters with the safety manager, so I know safety is very
Mhm.
important.
Yep.
Makes sense. No, it makes sense. I appreciate that. So, okay, so now we're thinking about the mining, refining. I like those because I normally think about like pumping, right, or drilling, or but I like that mining and refining petroleum. Okay, so first of all, it seems like that what we call conventional and what we call non-conventional really need to be switched, right? It's like what we call old and what we call
Old and
current,
new.
right?
Yeah.
Yeah, exactly. Um, and so then from a sustainability standpoint,
Yeah.
right? I think a lot of people would be kind of then asking that question, right? So like we do the new thing, great. And as I was kind of saying, like the tongue in cheek, right? Like, there's the folks out there like, well, you're going to make, gasoline out of corn, and how much does it really take to make that work from a sustainability standpoint? So from a fracking and oil standpoint, right, if most of it is no longer coming from just sink a tube and let the black stuff come out and rise up to the surface, instead we got to go in there and like scratch it out of there. Is there come a point where we're essentially like putting more in to get a little bit out? I mean, like what does that look like in the industry, and where is that at? Do you have any sense of that? I realize it's a little bit outside of the wheelhouse here, but it's sustainability in a broader sense, so it certainly fits into our audience.
Andy, can I address that question?
Sure,
This
sure. Got some
this is
thoughts.
one of my favorite areas. So basically, from sustainability standpoint, I want to tell you that there is plenty of hydrocarbons underground. It is just more and more difficult to produce it, but there is plenty of supply underground, and especially in the US. We are blessed in that respect. And I just talked about only three shales, but there are other such rock formations where there is availability of oil, and typically this oil is of higher quality than oil from other
Mm,
sources. And if you look at the API gravity, the lower the API gravity, the thicker, the more viscous, the lower
mhm,
quality it is. And the refiners, previously what they used to reject as something that they cannot distill, they are accepting those because
mm,
They are offered in the market at deep discount prices, but that makes the job of the engineers and operators much more difficult because it is much more difficult to process, contains a lot more sulfur. Okay, so these are called opportunity crudes. Okay, the other thing that came to my mind, and I think it partially answers your question, is why are we talking about this subject where we know that eventually the planet is going towards renewables and 2050 is the target year when it will be carbon free? Now, the reality of the matter is that the relevance of oil will never go away. From the statistics of several years, actually the oil production, crude production has gone up steeply. And that's mainly because the use of oil has shifted. Oil is now used more as a chemical feedstock than a fuel. You can feed your thermal power plant or your automobile from renewable resources, but you need oil to produce plastics, and now plastics have become parts of our bodies. So when it comes to petrochemicals, you cannot get rid of crude, and that's why crude production is going up. Now, similar thing applies to gas also. Although we are talking about carbon neutrality by 2050, it cannot be fed by hydrogen. It cannot be fed only by green energy. You have to have a hybrid situation, a combination of both the conventional fuels as well as renewables. So what's going to happen is that, and I have some statistics from a McKinsey study they're showing. And now what's going to happen is more and more CCUS will be utilized because from heavy industries, you cannot get rid of petroleum and oil and gas. So where will that CO2 go? They will go into the ground, into the rocks after carbon capture. So it will be more going towards a blue economy than a green economy.
Interesting. What was CCUS? Did you just mention an acronym? I wasn't familiar with
That
that.
is carbon capture and underground storage.
Got it. Thank you. Fantastic. And did you have anything to add on that one? Or
Yeah,
that's...
I mean, I like the maybe it's just this other part of the question, but is the shifting in the last few years at least of thinking about the produced water as potentially being a source of minerals, lithium, etc. I think that's a nice kind of way from environmental perspective to think of it more as that a resource rather than a waste. Always like those kind of discussions. So in the past it was, hey, we produce all this water, what are we going to do with it? Let's just pump it back in the ground, right? Oops, it causes some earthquakes, we can't do that now what are we going to do? So then it's kind of it's pushing that need to look at be more innovative and think it through a little bit more. Okay, now can we recover like lithium or other
It is more
metals?
critical for Permian Basin than for
Yeah,
Marcellus Shale, or because there is no nearby water body. It is all
right,
very drought-prone areas of
right.
West Texas and New Mexico, as opposed to Marcellus, which is in Pennsylvania, that has plentiful of rivers that can be discharged to, and also also the Bakken Shale, North Dakota. So there are water bodies, but
Right.
here
Out in the desert,
you
there's
have,
not a lot of place for it. Yeah. But and then also there's that need then for the water. So if you can kind of tie in the energy, the water need, and the recovery of salts, that's where I think people are getting more holistic in their thinking of how do we manage the water there. So
Yeah, I mean, just they're interesting things. I mean, I saw a presentation on the whole energy and materials cycle around like steel, and I was like, wow, it's like they don't have to go mine it; they just recycle it and you're like, oh,
yeah,
so
yeah.
it's actually really sustainable for something that you're like your intuition may not be that, right? And you're like, so then how do you apply sustainability to all these others? So it's now, so there was a question about the source of that pie chart for the water uses where you had, that was, so if you guys can dig that up, you may not have it on your fingertips, but, we did have a person that
I
asked.
will send it to you,
yeah,
Dan, because it came from one
how
of
can we
the contributors.
I could be cheeky and say it's in the book, but by the book you'll find out. No, we'll
Well,
dig
you'll
out
have
the
to
reference.
you'll have to explain to the rest of us in English that cheeky from your English means that
Oh.
you're
Yes.
not everyone will know what that means, right? So
That is Andy's English.
exactly a different
British
version
English.
of English, right?
Uh-huh.
So along these lines, right? One of those materials, so it'd be the ions, it's the sulfur. You talked about, the sour, right? But how about the heat, right? So that also was very interesting, right? So there's an awful lot of the water use in the refining process is basically heat transfer. Either it's makeup water or it's let's get rid of the heat, right? But I would imagine that part of that is okay, well, let's cool it down so that we can then get to the point of doing biological. So one is, well, let's do thermophilic biological, let's just keep it warmer. And the other might be, well, let's get that heat in our extraction, because I imagine the hot fracking fluid going down and breaking stuff up might even work better than the cold fracking. So why are we not trying to grab this heat, or are people thinking about trying to grab the heat out of the process?
Actually, in the industry, most of the heat is recaptured by feed effluent exchangers. When a feed comes in, the effluent from the distillation column comes out at high temperature. So the feed goes in at a higher temperature. Now, there comes the question of cooling tower, because cooling towers dissipate a lot of heat.
Right.
The more you reduce cooling water, the more you reduce the heat load, the heat burden.
Sure.
So that is definitely a very good point.
Yeah, because we still look at, right, we still think, I mean, like in a sense, a cooling tower is to get rid of waste heat, right? And so from a sustainability standpoint, we should just start to try to purge those words, right? There shouldn't be waste heat. There should be like, well, where can we reuse it and why? And why are we not? And there might just be efficiencies. It might just become no longer cost effective to try to deal with it. But
No,
it just,
actually, some of the things they are already doing it in the refineries. In long distillation columns, there is something up on the top which is the condenser, and the gas that comes out, that is condensed in a condenser using cooling water. That is the use of cooling water. Nowadays, they don't use water cooled condenser anymore. They use air cooled condenser. They use the air and the induced draft fans to cool the vapors that come out from the top of the distillation column. So instead of using cooling water, they use air for cooling.
interesting.
So Dan, I know it's not directly what your question was on the waste heat, but there's a gentleman called Kevin Lacey out of Cities Resource Recovery. Give him a little plug there. He's investigating. He came from the petrochemical industry, looking at fracking and whatnot, and then he realized about this thermal aspect to it. He's investigating in the idea of using kind of a deep well to do pre-treatment of biosolids. So if we do THP and all the rest of it, steam, you trying to use steam, he's like, well, it'd be much more effective just to pump the sludge way deep down, use that geothermal energy, and then bring it back up. And we now have the technology from all the fracking that's gone on to make that more cost effective than maybe doing a steam approach to something. So I think he's got one or two research projects up and running already, but I thought it's a really neat outside the box thinking of the technology in one application. Okay, now we can do biosolids treatment with the same kind of approach. I thought that was neat.
No, these are fascinating, right? I mean, it's a whole sustainability angle on the
Yeah.
existing thing, right? Because of course, like your mind goes to you Google. So I was of course Googling petroleum treatment with thermophilic anaerobic granules, and I'm like, oh, there's a paper on that. So you're like, oh,
Yep.
that's of course there's a paper on it. There's a paper on everything. We had a really technical question here, and I'll go ahead and read it and see if you guys can wrestle with this one. So sodium hypochlorite is used to oxidize the facility's refinery wastewater discharge to reduce sulfides. However, chlorination also oxidizes organics to form chloroform and other disinfection byproducts. And in addition, sulfides can facilitate the breakdown of organics. Increased chloroform concentrations and loading can increase their downstream POTWs, increase health risk. We were talking about that with sulfur. So two-part question. One, have you seen any alternative disinfection methods implemented like ozonation or UV or activated carbon or pH control or possible use of hydrogen peroxide to prevent or reduce chloroform formation, part one. And part two, do you know of any facilities or exemplars where they've been able to reduce or minimize chloroform loadings and DBPs by having any better control equipment or more precise chlorination dosing? So it's a very technical question, but one that board
I can
certified
answer
people get
that.
all the time. So
I can answer that, Dan.
yes,
Sorry,
sir.
Andy, let me address that.
Go for it.
So typically, petroleum refinery wastewater, process wastewater, the biology does not contain fecal coliform because it does not come from our feces. So you don't need disinfection, and they don't do any disinfection. Disinfection is only done to the sanitary waste on site. And that's why I told you that they do separately. The sanitary waste, of course, they do chlorinate and they do the normal disinfection. But that has to do with any domestic wastewater treatment system.
Mhm.
It's similar. But for refinery wastewater, they never do chlorination. They don't do chlorination. Okay.
Makes
So
sense. But yeah, but there's some sodium hypochlorite from some of the sulfides control, I believe. Was that something that was mentioned in there? I'm trying to recall. I think that's what part of what the question was looking at. Oh, I think he's buffering. We got him. Okay. Oh, we got him back. All right. There, you were buffering there for a minute. Sam, I was asking about the sodium hypochlorite that was part of the sulfides control.
you can use for sulfide control when you have hydrogen sulfide coming with the gas stream.
Okay.
Then you can use sodium in scrubbers like they do for odor control also in municipal treatment systems. Okay.
Got it.
But typically they don't use disinfection.
Fair enough. Fair enough. So then in terms of the wastewater treatment, so Andy, you were getting then to some of these modeling examples and all, right? So, okay, so if at the end of the day, it looked kind of like the activated sludge was a little bit of a polishing kind of, hey, we'll still clean up less some organics and some stuff, so we'll run it through either fixed film or suspended. But aren't there some BTACs? Aren't there some toxic compounds? So I know Sam was talking about whole effluent toxicity, which I tend to think of as like after the secondary treatment to make sure I can do discharge. But it seems like we're also maybe thinking about it before the industrial activated sludge so that you don't kill off your sludge process. Can you speak a little bit to how you dealt with
Yeah. There's a couple of, well, 2-3 aspects to that I could touch on there, Dan. One is in terms of the modeling of it. Maybe I'll start with that. Is there are various modifications to the biokinetic models that we use that uses slightly different kinetic expressions to look at whether it's inhibition, that it's preventing growth, or even direct toxicity. So again, in the book, I should push it back there, we kind of talk through the different formulas that are available to kind of manage that and understand that. On the practical side of it, treatability testing is very, very important when you're looking at biological treatment. So doing testing of, okay, what level of contaminants can we manage? And then there is, of course, the classic understanding of acclimation. So if you grow the right microbes over the right length of time, then the BTECs, et cetera, you can manage them to a certain higher level than you would than if you were kind of shock loading them, or if you went to your local domestic plant and dumped a bunch of BTECs there. So you can grow the biomass and the consortia of microbes that you need to manage what your waste is. But yeah, doing toxicity testing and treatment testing is an important part of understanding that. And then you can put it into the model to kind of model it and size things appropriately. Yeah.
And Andy, if I may add, this is the reason why in refinery wastewater treatment, regulators call for TOC, not BOD, because I personally experienced a situation, this is for Shell Singapore refinery, where they were complying with the effluent BOD, and the BOD was less than 5, so there was no problem. Then the regulators came back and asked them to check the COD. COD was above 100. And that says that there are many chemical components that were passing through that were not biodegradable, so they would not be registered by standard BOD test.
Mm.
So then they came up with the TOC. And of course, TOC measurement is much faster than BOD. So they got rid of the BOD.
Makes sense. Makes sense. So kind of final question. So for folks that are coming, that are listening to this, right? So some people are right in this space, right? And then others might be students that would say, hey, I want to get into this space, or others might be working in other areas and say, hey, industrial waste, there's some options for me or things to get it. What advice would you have for folks that want to get into, we've got people here with a 40-year career, a 30-year career. I thought maybe it was a competition to say who could, who's been working
Who's the oldest guy
longer.
here, right?
Who's
Yeah.
the oldest person here? Not
Yeah.
it. So what sage advice would you find folks, friendly gents, as I described you at the beginning, give for those people who are thinking about this?
I like that. I'm normally the old guy these days, but then some you kind of a mere 30 plus years. You got your 40 plus. I don't know. Certainly, I'd like the idea of thinking more in terms of sustainability, life cycle, circular economy type stuff at the college level. But then from an industry point of view, how do you get into this space and understand the water side of it? I think it still is through the kind of traditional route of chemical engineers being hired by some of the big players in the market, the Chevrons and the Shells of the world. So I think that is the most logical pathway. Association of Chemical Engineers, they have groups focused on water specifically. So that's a good organization to get involved with. Do you know the name of that SOM? I've forgotten the name of it. I presented there last month and I've forgotten the name of it, but there's a group. They met in Houston this year. There were some good presentations there.
Is it like a one-off, or is it like a subject matter expert, a special interest group like within AICHE or somebody like that?
Within AICHE, there's a water group, right?
Okay.
So
Actually, I would say, Dan, that someone, especially for those who are entering the field of water wastewater treatment, I think a good entrance point is domestic water treatment, wastewater treatment, because that gives the foundation. Because industrial wastewater treatment, we talk about toxicity, we talk about various things that are more complex, but we need to have a clear understanding about the fundamentals of water and wastewater treatment, starting from the Metcalfe and Eddy book. That's how I started from domestic wastewater treatment, and then I moved on to industrial. So there are certain nuances with industrial waste treatment, but I think a good foundation is domestic wastewater treatment, the Metcalfe and Eddy book, and then of course go and read our book.
Of course, the shameless plug.
It's kind of like the basic classes to do domestic wastewater, and then industrial gets a whole extra level of complexity and way more interesting things to look into. So
and each industry is different.
Yeah,
each industry is different.
Yep.
You go to textile industry, that's different.
Very different. Yep.
Food industry, very, very different waste streams. Very, very different waste streams. Now, this is fantastic. Well, gentlemen, thank you so much for taking time out with us today. We really appreciate having you here, and I will turn it back over to Marissa.
So let me share.
Thank you everyone for all your questions, and thank you to our speakers for sharing your knowledge with us today. We have several webinars planned in the near future, so you can go to aaes.org/events and reserve your spot. Just a reminder, if you're not yet a member and you're considering joining the Academy, you can email me to discuss our membership options. And for all board certified individuals, PDH certificates for this event will be sent out by the end of the week. That's all for now. We enjoyed being with you all today. Thank you so much and have a great day.
Thanks all.
Thank you all
Cheers.
for attending.
Bye.